So hello friends, today what we will be doing is learning how to implement RCA 4-bit using full adders. So the main aim for this is to teach you how different data flow and behavioral models work, how to implement such different styles of coding, and also how to get your first project done, so that you learn a lot. So let's get started. So I am adding a full adder module, a Verilog module. Next, so I have a file over there, but we will replace it, no problem, starting from scratch. So there are two different ways of declaring input and outputs to your module. See, the first one I will show you is here. Using this UI you can either declare the inputs, you can say if it is an input or output or in out, but and then it will automatically add it over here. But what I would recommend is use this style. So we have 5 variables. Now we have input A, B, now single bit variables, right? And if you want to declare them as some 4-bit variables, we can do this like 30, but we'll do this when we will build the RCA module. So we have outputs, output sum and cout. So first of all we will be implementing data flow style, data flow. So what we can do here is we can use variables, but in data flow model you have to use wire type of variables. So wire temp, and when we add two single bit binary numbers, the output can be maximum of 2 bits. Like we add 1 plus 1 then 2, so binary of 2 is can be represented in 2 bits. So we are creating this temp variable of 2 bits. So in data flow you have to use keyword assign for assigning the values. Assign temp of 0. The indexing of the variables is the same as what we do in C language or any other languages, right? So here we will A plus B plus C in. So the addition of the single bit sum will be inside temp 0, and the carry out, so no, let's not do this. Okay, so right now the temp variable has a 2-digit number. The LSB of temp, that is temp 0, is carrying sum of those 3 numbers A, B and C in, and the MSB, that is temp of 1, is right now carrying the value of carry out, right? So let us test this module. So for this we will have to build a Verilog text fixture. Let us name them as full adder underscore TB, so that we can know that this is a test bench file. Replace it, starting from scratch. Select this module for whom we are building the test bench, so that it can set up something for you like a reg, a wire, and these all are the pre-set up things by Xilinx. I will explain you why they are there later on. So A is 1. Then you might be thinking, if like here we are giving decimal 1, but a decimal number can be of 32 bits also, right? But our variable A is a single bit, but Xilinx does this job for you, but you can also specify the bits of a number, like you can write 1b 1-b 0. so right now you are specifying it that b has just one bit of number 0, the last bit of number 0, right? So you can also do this like 1b dash, sorry, 1 dash b. I always forget this. So we have 1 0 and 1, right? So we will save this. We will go to this simulation, select the test bench, run behavioral syntax check. Once it's done, we will be simulating this model, and let's see if the output is correct or not. So we are adding 1 plus 1, that's 2, right? So sum should be 0 and Cin must be 1. Yes, so carry out is 1 and the sum is 0. So yes, this is working. So next what we should do is we will add a 4-bit RCA 4-bit module, and we will be importing this full adder module over inside RCA 4-bit. RCA underscore 4-bit, another module. Yes, replace it, starting from scratch. Yeah, so again here we will be declaring inputs and outputs of RCA 4-bit. so we have again sum, say out, A, B and Cin, right? Excuse me. So input, so we have our inputs right now of 3 bits, right? A and B are right now 4 bit. So A, B, and then our Cin is just a single bit input, right? Similarly output sum, but sum is also 4 bit, and then output say out. That's it. So what we'll be doing is calling the modules adder, full adder, then initializing the object by naming giving some name f0 for, let us for now. Then we should call it by, now we need to pass the variables in the same sequence which are declared in full adder. So for full adder we have first one sum, second is C out, and then we have 3 operands A, B and Cin. So we should enter the variables in exact same order, right? So we need C out, right? C out, but C out is the one which comes finally out. So here we need to use some temp variable, and then we have A of 0, B of 0 and Cin, right? Cin goes for the first time. Then we have to call this for 4 times, right? So beginning, then let's someone, so temp goes in, yeah, but there is cache over here, that is you cannot reuse variables. Like I am giving C in for this full adder, the temp variable I am giving as an input, and also I need the output inside temp variable, so this is not allowed. So we need to do something for that, and I am right now we are in data flow model. We have this code in data flow style, right? So I will use wire then temp. So like let us build it for like 3 bits. We will need 3 variables, right? I think so. Let us see, if we need more then we will do some changes as per the needs. So we have temp 1, Yes, so let us copy this down, and we need to call two more ones, right, for MSB and the second last bit, that is sum2. Then we will be using this this the output of this full adder as a cin for this, and here we will be storing it in temp2. So again we need to do this change in indexes. So right now we are going for bit 2s and 3s, and so here we can use directly cout, right, because this is the final carry which we want. So that's it. And this temp1 no temp2 should be there. The output of this adder should be an input carrier to this, so giving some different names to these modules, and that's it, we are done. So now let us test with this module by adding a new source. We will be building a test fixture. So RCA /tb, so that we can remember that it's a test bench. Yeah, we will be starting it from scratch. That's it, finish. So now we have to put the values over here, like A is a 4-bit number, right, so we can have 12, and then B can be what we need to put 4-P, that's 0 0. So let us put 0 0 1 0, that is 2. Yes, binary of 2. Cin, let it be. Yes. So now after 100 nanoseconds, let's change the values of, like D can be now 5. So 12 plus 5 is 17. We will need now a 5th bit to represent a 17. So cout should be 1, right, after D is 5. Yeah, so we are done. Let's go to simulation, select this test bench, run behavior, check syntax, and then done. Simulate. So yes, now yeah, so after 100 nanoseconds the cout is 1, right. Okay, let us do this. I just love this, simplify. So 14, right, so we have 12 plus 2, 12 plus 2 is 14. We have cin 0, so 12 plus 5 is 17. So this cout is 1, and then we have a 17 has a binary of 1, then 3 zeros, and again a 1. So total 5 bits are there. The 5th MSB is stored in cout, and the 4 bits, that is 0 0 0 1, that's in sum. So 0 0 0 1 is decimal, goes to 1, right, 0 0 0 1. That's it. Thank you.